Yes. I'm trying to go to full screen. So as you can see here, we have two systems to demonstrate. One is the aluminum zinc system, another is NiAl-MO system. In both we will show precipitate growth and coarsening. First, we will show cases of single precipitate growth. Then we will look at coarsening, and in coarsening also we will look at multi-step aging type of a problem. One particular problem of multi-step aging. So we'll go step by step. Remember that in the previous day, Avik was demonstrating the GP model. Today, Mohan demonstrated the KKS model. So we are following a KKS type of formalism, but very similar to the. It's basically this very similar in terms of the physics that it captures. So I'll just give a very brief overview of this thing. So it's all it's all there. I do agree. I don't want to give all this. I don't want to make you scared. So I just wanted to tell you that we have the total free energy, and it's a multi-phase, multi-component system. So you have to write the Lagrangian. So this FL is the Lagrangian. So you have F local, F gradient, and this lambda 1 minus h 1 minus summation of phi. This is because summation of phi. This is over all phases should be equal to 1. And the F local can be approximated as it was demonstrated yesterday using this double well or double obstacle potential. We use not multi-well potential or multi-obstacle potential, but we are using multi-well potential. But there is, in the later versions, we will also introduce multi-obstacle potential. And the free energy, as has been given in the manual. So that is what I wanted to tell you. The free energy we are getting from the exact free energy from the databases, the open databases for aluminum and zinc. However, there is some small issue with the F2 function, the exact function when we go to multi-component, because the Newton solver is not if the GSL based Newton solver is not available on CUDA, so we have to write it, and there are some issues there. But FN-F3, which directly reads the curvatures and the phase compositions from the open database, and uses a parabolic approximation that works perfectly. Also, from encrypted databases, as was mentioned, FN-F4, the function F4, that also works perfectly for our system, where basically we are, for different temperatures, we are basically giving the phase compositions of the precipitate phases, the precipitate phases and the matrix phase, the parent phase, and we are also listing the curvatures of the free energies. So now there comes the So in KKS model, for example, there in a grand potential model, they are looking at the grand potential equality. In this case, what we do in KKS model, the constraints are the diffusion potentials have to be equal across phases for all species, and also as you know, this is the composition. The CK is basically a sum of HI CKI, where K is the K denotes the species and I denotes the phase. And then we have these two governing equations. One is the Allen-Kahn equation for evolution of the phase fields, and then there is the diffusion equation, which is for the evolution of the composition fields. So these are solved together in a coupled way. We have the Allen-Kahn equation, the diffusion equation, and this constraint equation. So these are all solved together as a result of which the microstructure evolves, the phase boundaries evolve, and the microstructure evolves. One very important thing I want to tell about tau and tau epsilon. Tau is a relaxation coefficient. You can also write this in the form of like del phi del t equals minus L. So L there becomes you called it like that L is just an inverse of the tau epsilon, and you can think of L as the interface kinetic coefficient. So kinetic coefficient and relaxation coefficient. The idea is very simple. If you have diffusion control growth, you require to have infinitely fast, means if you think of diffusion control growth, then if you look at dynamic Gibbs-Thomson equation, then you can easily understand that the dynamic Gibbs-Thomson equation goes to the equilibrium Gibbs-Thomson equation in the limit where the relaxation coefficient goes to 0, and that actually gives us the relation between the mobility, means what type of tau value we should choose. So you can have different types of, you can choose tau values which will give you completely diffusion control growth, which will be restricting here, but you can also choose tau values which will give you mixed control or interface control. In the case of interface control, remember that the diffusional, so what happens is all the energy is basically dissipated by transferring atoms from across the interface, and you do not recover the equilibrium Gibbs-Thomson equation. So here, for demonstration purpose, we are looking at fully diffusion control, and there we will also demonstrate the Gibbs-Thomson effect. Gibbs-Thomson effect, as you know, is draw. Okay, it's okay. So I will show you when we'll demonstrate. We'll show you that what happens is, if you look at the phase boundary compositions in this phase diagram, you look at this. Say, for example, we are looking at this FCC A1 HCP A3 phase, and think of this temperature T1. I am at temperature T1, which is at the solvers, and now I could put it to T2 and I hold it there. Now what is happening is, if I had, so all this entire phase diagram is constructed assuming a flat interface, a completely flat planar interface between HCPA1 and HCPA3. Now, however, the HCPA3 will be forming, like in this case, we are assuming isotropic interfacial energy. They will form like the circular droplets. These circular shapes, these are forming. You have an interfacial energy associated with, and there is a creation of surface area. This is compensated by the change in the bulk free energy minus delta G. So the idea is that when you have this spherical precipitate, with this convexity, so what will happen is, because of this gamma kappa, you will have a shift in concentration. So the shift will be all, in this case, the shifts will all be on the right side of the phase boundary. So you will see the matrix side as well as on the precipitate side, the compositions, the equilibrium compositions will shift to the right side. With the free energy composition diagram at a fixed temperature, you can basically very easily relate it to the tangent construction. There is a change in slope, and that change in slope you can basically equate, and you get some very simple relation like this one. So the change in the matrix composition, for example, at the interface is given by gamma chi. This chi is basically the mean interface curvature, and there is this zeta m, xi m Cp equilibrium minus Cm equilibrium. This is for the flat interface, and xi m basically gives you the free net, the curvature of the free net function, del 2 del c square. And remember, the curvature, the two free energies that represent the matrix and the precipitate, they can have different curvatures, right? So if they can have different curvatures, so if you know delta Cmi, you can get delta Cpi by using xi m by xi p delta Cm, and that is the shift. Remember, only very important thing to remember, that in these cases we are looking at all convex shapes, very regular convex shapes, whether it is circular, elliptical, and stuff. So you will always get a positive shift in the positive shift in the composition, right? Compositions will shift to the right, the equilibrium compositions. However, there are cases, for example, phase separation, or there are cases where elasticity can drive to concavities, and in such cases, when you have concavities, the composition can also shift to the left because of the capillarity. So we will look at that one by one. So this is something that I wanted to emphasize. This is again regarding the tool, that function F2, when we did two-phase two-component test, please note that this will not be released, the two-phase two-component test, but yeah, we are trying to quickly correct this multi-phase, multi-component Newton, and we I think, but it's still a work in progress. We are trying to fix this Newton solver, because there are some small issues about convergence that we are seeing. But when we did the two-phase two-component test, if you look at this, the exact and the parabolic did not show any difference. So basically, we can tell you that the parabolic approximation definitely does work. However, the exact thing has some issues in our solver, so we are trying to fix that. So so the FN F2 and FN F3 works. sorry, FNF3 and FNF4 works. FNF4 is the encrypted database one, and FNF3 is the open database one. So those versions, and both versions we are using parabolic approximation. Only thing in the encrypted database one, you cannot read the database. As a result, you are basically storing it as two CSV files. One CSV file contains the curvatures, which is already demonstrated, and one CSV file contains the phase compositions at different temperatures. So and now there is a very important thing here. Saurabh will basically. Saurabh, you want to build something? Yeah. So remember, this is a very important thing that we have to tell, because we had access to Param Seva, Param Sanganak, and Param Pravega, and we found out the issues are CUDA aware MPI must be there, which is there in all these Param clusters. So if you want to use in your own cluster, then basically you should install a CUDA aware version of MPI, and the CUDA version should be 11.x to work smoothly. Otherwise, there are lots of bugs, and there are lots of bug fixes there in GitHub, but it takes a lot of time to compile. But if you go to the higher version of CUDA, by the way, now most of the CUDA, all CUDA is, I think, recent CUDA version is 11.6. So CUDA 11.x on 11.0 onwards, there is no problem. But you require a UCX version 1.4.0 plus, and this GDR copy. So you want to, yeah.
GDR copy is an NVIDIA library that it's a framework that enables efficient transfer between GPUs using their RDMA technology. So that only comes into play if you have multiple nodes. So if you want to run on a single node with multiple GPUs, like say an A100 DGX machine or so, you can just install UCX without GDR copy. Installing UCX is a simple process. You can go to their GitHub page and clone it. They're given instructions. 4 commands you have to build and make installer. Then you have to, if you already have OpenMPI installed, there is a script in the KKSFT CUDA NPI GitHub repository or CUDA aware test.c, which you can use. It's a simple script that you can use to find out if OpenMPI, your OpenMPI installation has CUDA aware MPI enabled. Now, if that returns a message saying that this system does not have CUDA aware MPI, you'll have to rebuild OpenMPI using UCX. So you have to install UCX first from their GitHub page, and then rebuild OpenMPI 4. Whatever. I've tested it 4.0.5, and then so yeah, you have to rebuild OpenMPI with you, and then test.
Yes.
It should return time, and at build time, CUDA aware MPI was found on the machine, and that is all you need to run OpenMPI plus CUDA aware.
So another thing, yeah, this is actually, this should have come before. This slide should have come before. You first need to check wherever you are running or whichever nodes you are accessing, all should have the NVIDIA compiler installed. If that is not there, the NVIDIA, the CUDA toolkit is not installed in all the GPUs. Means all across all GPUs, you should have the NVIDIA. Means NVIDIA should be able to detect a CUDA enable card. If it is not there, and you have installed in one machine, say CUDA aware MPI, and you want to run it, then the problem is that you will suddenly see some error of segmentation and stuff. So this is something that you have to remember. One thing is definitely sure, if you are having this type of clusters, you will not basically do this, that you will have some node list where these GPUs will be there. You have to choose from that node. That's all.
Can I elaborate?
Yeah.
So the reason CUDA aware MPI is important is because without that, you'll have to stage all your data from each node, each GPU. You'll have to stage it to the host.
Yes.
So now it is possible to run without CUDA aware MPI, but the data transfers will take a lot of overhead by themselves. So now CUDA aware MPI will directly, it's aware of the GPU, so it will transfer between GPUs without staging it to the host. So one MPI send receive call, you can have an MPI send receive call between GPUs rather than between a GPU and host, and then host to GPU, anything like that.
Yeah, so basically you are skipping the host. Yeah, that's a very important thing. But if you don't do that, actually these codes will not have the efficiency that generally we expect. Because if you have to run through host, means you have to every time you have to go through host and then go to GPU, then the entire a lot of advantage is lost, right? Particularly for very large sizes, the advantage will be lost, and you cannot use a large number of GPUs and stuff. So be aware that, and CUDA or Ampere, by the way, is there from 2003 onwards, or 2000, right? 2000.
No, it was created in the last decade.
So okay. So yeah, Shourov is the whiskey here. So I'm just telling the physics part of it. Shourov will tell all the software part of it. So he's the guy. We have to ask questions regarding all this hardware and all the software needs. So yeah, previously we had KK's CUF50, but now it is case, and so we are just keeping it. The first line we are keeping because later we will have both KK's CUF50 and CUDA, this final difference CUDA code that we have, because the elastic code generally works very well when we use 50 libraries. So elasticity integration, that's why it's still remaining. So, but again, KKCU50 also will require CUDA versions 11.0 plus, and there are some flags basically for Pascal and for Volta and for Turing and the new Hopper and all. So those are the flags you should use if you want further acceleration. So we are using, so for similar to the CUF50 library where we use CUB library, here also we are using the CUB library. CUB library is a very fantastic library for, again, Shourab can elaborate further. So CUB's advantages and all.
So CUB can basically do all reduction operations for data without you having to write kernels for it. These are highly optimized. Even if you try to write a kernel, it's very likely that CUB will outperform your kernel. So usually it's recommended to use CUB for, say, if you want to sum across all your elements, or if you want to find the min max. And there are a lot more operations, but for our code, we have only used min max and sum. I think there's a little bit of elaboration here, which I'll get to in the next slide.
Yes.
This is how we are implementing our kernels in CUDA. So all the for loops become, so you don't need to write for loops. What CUDA does is it calls, say, up to 1024 threads per block. So it will distribute the block across all its cores by itself. You don't need to do anything except for telling how many blocks you want and how many threads you want per block. So it's similar to domain decomposition in MPI, except it's done implicitly by the GPU itself. So now, when you're decomposing across GPUs, you have to have a buffer layer, because in finite difference, you'd want the neighboring, the information about your neighbors. So for that, we can do 1D, 2D, 3D domain decomposition as has been done in the NPI code. Right now, since our number of GPUs is small, I've stuck to 1D domain decomposition, which I have only, say, if we have X, Y, Z, 3D, I've only decomposed along the Z direction. So where MPI comes in here is to transfer the buffer layers, which you can see are marked in blue on the left, between GPUs. So the buffer layers are something which had to be taken care of, since we don't really need to transfer them between. We don't. So I have them only on the GPUs. I don't store them on the CPUs. So I transfer them directly between GPUs.
Anything else?
So I think that is the, so yeah, that is the salient point here.
So let us go to the demonstration then.
Yeah.
So we will talk about this. So there are some models, as you know, every model has a model specific input. So in our case, the model specific inputs are like tau, epsilon, T equilibrium, and T. We will demonstrate now. First, we will start demonstrating with a aluminum zinc single precipitate growth. So we will, again, as I told you, we will at 550, which is like solver's temperature. That's the equilibrium temperature. From there, I am quenching to 450. We are giving 100-degree undercooling. I'll go to the first slide. Yeah. So this is the idea. So if you look at 550 and this is 450, so we are giving an undercooling, and as you can see here clearly, as you can see here, that as soon as you give this undercooling basically gives you the supersaturation. The FNF3 basically is written in such a way that this undercooling is recognized by the system, and and as a result the supersaturation is there, and as a result of the supersaturation the precipitation will flow. So let us see. So we will first generate an in file, and we will first generate an in file. You some size. Yeah.
So you just go. Okay, is it audible? Okay. What happened to you? Go to Teams. Speak. Speak. Hello. Hello. Yeah. Yeah. That's good. What happened?
This GUI has.
Just share your screen. Oh wait. Yeah.
Screen shared, right?
See, you can see here. It's not appearing.
No, screen is shared.
Just unshare and then share.
Yeah, now it's yeah. Not generating. So we'll generate from scratch.
So take a 256 square system.
Yeah.
Keep this open. 5 minus 10.
Increase the font size.
No, that's a reference input
Okay.
file.
It's not working.
It's very slow.
From here are you?
On my laptop.
Why is it so slow?
Sort of importing.
Import the input.
Okay.
Go back. Go back. Alright.
No, that it was stuck. It was stuck. Oh, I know what to do here.
Yeah, because there is that we are doing it from SSH remote. That's the main problem. Somehow the network is not working as well as we expected. Otherwise, just let us see. Import it. Can you import?
Yeah.
Import it. Import.
One second. So there are two on. So I'll import. So we'll use 256.
Yeah.
5e minus 10, 5 minus 10, 1.
So
delta T
please
will-
tell. No, you have to tell.
Yeah.
So this is like 0.5.
Yeah, so these are all dimensional. So this is 0.05 nanometers.
Okay. Continue. 0.5 nanometer.
0.5 nanometers.
Yeah.
Yes, sorry.
0.5 nanometers. Yeah. Continue.
Then delta T will be 2e minus 8 seconds. So that is 20 nanoseconds. We'll have alpha and beta.
Yeah.
Here, one thing to notice, the alpha will be the matrix phase, beta will be the precipitate phase,
Right.
which is FCCA1 and then HCP-A3 respectively. Our components are AL and ZN. We'll run it for 10,000 time steps.
Yeah.
No smoothing, and we'll save every 100 seconds.
100 steps.
100 steps, sorry. Don't need to do all this. So our diffusivity will be 1e minus 13. Elasticity is not relevant right now. We can set same as previous. Gamma we will take around 0.1 joules per meter square. 8.314 for R, and molar volume will be, we can take 1e minus 5 meter cube per mole. We'll test function F3 first, which is the direct TDB integration.
Let's show the TDB file, please.
So we'll take ALZN MEY.TDB. The TDB phases will be matrix and precipitate. So FCCA1, HCPA3, FCCA1, HCPA3. So these I have already input. C equilibrium and C fill will be what we are filling with, and C guess will be the guess for the equilibrium values at the simulation temperature, which will specify later. Rotation matrix.
So that means the C equilibrium is at T550, and at T450 is where the C gas is, right?
Yes.
Yeah.
We'll set same as previous. We use periodic boundary conditions, so
Yes.
we don't actually need to do this, but for completeness we will. We'll fill a single cylinder. Since our particle is beta, we'll say. See, there's a bug here.
What happened?
Filling, there's a bug. It's a bug on my side, I feel. So I have a filling file ready, so I'll use that. We'll fill a single cylinder of radius 12 at the center of the domain.
Yesterday it was working.
So we'll fill, right format will be ASCII. It's not very visible here because of my fonts. Very sorry about that. We'll track every 100 steps. Relaxation coefficient will be, so tau will be 5e13. Epsilon, which is the interface width, we can take 8 units, 8 grid points. So since our dx
8 nanometers.
no, 8 grid points. So since our dx was
0.5.
0.5 nanometer, we'll take 4 nanometer as epsilon.
4 nanometers.
Equilibrium temperature is 550 Kelvin. We'll simulate at 450 Kelvin. So I will call this ALZN F03 single. Generate the files.
Yeah. So what we will do? So one thing, please note that because there is some problem in the cluster, as Mohan also told, directly running is difficult. So we are generating the input file. We will show you the input file, and then we will run it from the console, as Mohan has already demonstrated. Right? So
Yeah.
So please show the folder where you have saved it.
Yes.
Show the filling, and yeah. Can you increase the font? Yeah. So if you see the filling, please.
We will, since our domain is 256 square. I'll change this to 128 and 128, which is the center. We'll take a particle size of 10 to 12.
15 is also.
I'll take 12. So I just have to SCP the file. Give me 1 second.
Yeah, so this is the problem. So we have to SCP lots of files. That is something that you have to bear with. What we'll do is later we'll once these things all this remote running is the main problem that is happening here, and because we are running everything on the cluster, so that's one of the things. Can you increase the font size?
Yes.
Font size. Yeah, font size nobody is able to see.
So I have input ALZN F03 single dot in over here. First we will make clean. Make. Before making, I have to show. So for our specific cluster, again like Mohan did, we had to add some GSL flags. We use GSL for function F4. Here I've added the gen code, which is the specific code generation. It optimizes according to the GPUs. So this is something, if you want to optimize for your GPUs, you'll have to use the corresponding one like we explained in the presentation earlier. And all this is the compilation steps. So the modules we require here are CUDA, GCC, and OpenMPI. We have done an install for all users, so we don't need to use module load here for our particular system.
So later we will also show this this portioning and stuff where we have already done the simulation. We will show how the post-processing tool works and all. So here we want to show one case where you are running and then you are using the post-processing tool in the GPU. And yeah, so. Yeah, so you can now see running. You can see the composition values, and as you can see, you will soon see the Gibson something. I will demonstrate. Right. Huh?
Okay, this ran for 10,000 steps. So since it's an MPI based code, we are writing all the data separately like in the other ones. This is older data, so you can see here we have 10,000.
Yeah.
Just remove the old data. Oh, that's old data. So we have 0 to 10,000. This will be, so since our domain decomposition is in 1D and we have run with only 2 nodes, this would be the, since it's processor 0, this will be for y is equal to 0 to y is equal to 127 and x is equal to 0 to 255. Similarly, processor 1 will have the upper part of the domain. So now we can stitch it together. For stitching, we can just do make reconstruct first, compile the reconstruct. So then we have to do reconstruct.out. So if you don't give the correct arguments, it will, you can just run it like this and you can just run the output file and it'll tell you what arguments you need. So our input file was ALZN F03 single.in. We named our output as output ALZN F03 single. We have 2 workers, start time 0 n time 10,000. So it will stitch everything together. This is a much faster process if you have an SSD. Here it's a hard disk, so it takes a little bit of time. This is an SSD. My laptop is much faster. Good. Okay. So now we have the data. Unfortunately, this particular cluster doesn't have a working installation of ParaView because of some X11 issue. But we have another cluster where we can do it.
So our clusters are, so that is often often happens even in Param, the NSM machines, that the clusters that where you run, you cannot visualize. So you have to transfer the data to a visualization cluster. So very similar setup is what is followed in our place also in IIT Hyderabad. The way we have set the cluster. So he has to just, it is very fast. It will immediately go there, and we will open the post-processing tool there, and we will show you how the precipitate, all the different properties, like how the radius changed with time, how the area changed with time, and everything. Minus P patch.
Oh, this is transferring from the. We require the input file as well. Okay, so now we're ready to visualize this using MicroSim, the GUI.
Go back.
Oh, this is the other one.
There was, you could have gone.
So, no, that was on my system.
Oh. And then
This is over my mobile data, but that should not be an issue though.
so this is a small, so it's now working, thank God. Yeah, so do that also. So import the,
yeah, first I'll import the input file.
yeah.
Should be this.
Hold on.
It's slow.
Okay. No, did not. This one.
It's loading. There are 100 BTKs, 101 BTKs to be loaded.
Yeah. Now just run it. What do you want?
Oh.
It's going.
Yeah, it's very slow.
Very slow growth. So we should have run some more. We can do the other one. So we can just show at least the area and the stuff.
Yeah.
It is changing, definitely. Running.
Yeah.
Yeah, it's growing. plot all is
I can do plot all.
no. First let's do one by one. Yeah, first let's do the radius. What happened? This is what?
The radius.
Radius should go this way. What are you telling?
But I'll open the existing data that has more time steps.
Why is it shrinking?
No, initially when the interface is forming, there'll be a little bit.
Okay, so maybe we have to run it for a longer time.
Yes, we have to run
Okay,
for
so
a-
run the existing data.
Yes.
So we have a much larger simulation. So we will show that because what's happening here is we could not run a very long simulation, but it will show growth. I don't know. Can you show a larger one?
Yes.
So the exact same thing with the 512 by 512 system we have as precipitated at the center. Again 550 to 450 undercooling, and we will show you how it works. There it is clearly there. Can run it. Yeah. Zero. Whatever.
This will take a little bit of time. Meanwhile,
Yeah.
we can go ahead and.
No. Let's see that. Yeah. Let it load. Oh, can you open it?
No, it has to load everything, and only then we can. There are 1 million files.
1 million files. Yeah. So we have 1 million files, but you can see. Yeah. Now you run it.
Not 1 million. 1 million time steps.
100 files. Yeah. Now you can clearly see the growth. So it was. So you can clearly see the growth, and now you can also see. How we will show you. First, let the movie continue. But you can also see that now it has gone beyond growth, and you can see that there is some difference in overlap and stuff that is happening. So we can stop it now, and we can now see that the time. Yeah, you can. Yeah. Huh? Stop. Now do the radius. What happened? Oh, okay, I got it. Beta, do the beta.
Oh, okay.
Yeah, continuously doing alpha. I told you to be. No, see, please understand that. Yeah, the phase field nuances he's learning. So, but he's he has done a fantastic code. So what happened is he's choosing alpha instead of beta.
But
No, you do beta.
yeah.
Hey. But it worked. It worked. No plot.
Oh.
Okay, good. So one this thing that has happened. So you can see it's a parabolic growth, but now you can see also that it started overlapping. Diffusion field started overlapping and stuff, and then suddenly this change.
Actually, that point I changed the temperature.
Oh, okay. Okay, so please demonstrate. Yeah. Okay. Tell
So
me.
this one I had done. I had run at an equilibrium temperature of 550 at a simulation temperature of 450 for 500,000 steps, and then I had changed it. The temperature I restarted from 500,000 with a higher temperature of 500 Kelvin.
So what happened is, if you go on running this, you can see that it initially grows, right? When you go to the higher supersaturation, as you can see, the phase diagram. So you are going to higher supersaturation, it goes. Now you again go up. Now if you go up, then the basically solute has to be rejected and the particle shrinks. So that is the part where the particle shrinks. But let us not look at the particle shrinking part right now. Let us look at the parabolic growth. Now if you plot that side and look at the area change with time, you will basically see a straight line, r square versus t, right?
Yes.
Yeah, can you just show? In both cases it will happen. So, yeah. So you can see a very clean straight line that is there. Now you can also show the profile, please. At some stage at the time, we will show the profile, and we can the aluminum concentration. You can see that to demonstrate the Gibbs-Thompson effect, we want to show you.
So this is 512, 512. So end it at 256, 256.
Yeah. Yeah. Now you have to
Yes.
put the level. Yeah. Remember that the level that is there is a generic level. We have to make the change the level to this aluminum concentration. And as you can see that at the interface there is a shift, and here it is plotting aluminum. If you plot zinc, zinc will be going higher, and aluminum, as you can see, aluminum is actually lower in the precipitate. So aluminum is going down, but going more below the 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 planar equilibrium. So that amount, the delta C, that I have the formula. If you can use that sigma that we're using, 100 millijoules per meter square, right?
Yes,
Sigma and
point,
kappa.
point
So
one
and kappa is basically 1 by r, because it's a precipitate which is circular. So you have sigma kappa by del 2f del c squared. That is the free energy of the beta phase at the beta composition, at the beta equilibrium composition, times c beta equilibrium minus c alpha equilibrium. You will exactly see. Actually, it's means we plotted a few and we saw it's almost falling on the analytical the analytical value. So you can see the shift and you can play with the shift. Remember, the shift will happen opposite when you go to the other side of undercooling. Means you are going down. When you are going down, you have this but the shift will happen the other way when the precipitate is basically the precipitate, as the precipitate grows, the shift comes down, the Gibbs-Thompson shift comes down, and as the precipitate shrinks, again the Gibbs-Thompson shift will go up. So that is one thing that you will have to follow. And the precipitate will shrink when you're undercooling, means you are opposite of undercooling, means you have gone to a lower temperature, now you are raising the temperature. Basically, you are going towards the solvers. Now, if you go towards the solvers, precipitate is shrinking, then it will go the other way. Now we will demonstrate. Means please note that we could have demonstrated these runs or coarsening, but it becomes very difficult to do that. So we will demonstrate. So we have the coarsening simulations already, right?
Yes, but we should show the input file.
Yeah, show the input. No, that's what we'll do. We'll show everything, but we will not run it. So if we run it, because it's a very large, but we can show how to run it also, but it will take a long time for looking at appreciable coarsening. Yeah,
Import.
we will import. So the FN F3 LZN.
Yeah.
Then we will go to NILMO. That is another very important thing. Okay.
No, so that shift downwards is quick over if you're running on your own system. Over the network, there's a lag effect or something.
Yeah, so that's why it looks. We will also show, that is another thing that we will also show for NILMO, and there also you can see all the plots together.
Okay, so that's an older in file. So what we're going to show is 1024 into 1024 is the domain size.
Yes.
We will take a delta x again of 0.5 nanometers and a delta t of 50 nanoseconds. Our phases will again be alpha beta, where alpha is matrix and beta is the precipitate. We take aluminum and zinc as our components. So
2
we
million
have,
times.
yeah, this is 2 million, but the data I'll show you, it goes all the way to 6 million, which is where you'll see appreciable coarsening. Start time we can give 0. Restart as 0. Again, diffusivity will give 1
So
minus
that
13.
is another thing that is there in our tool. This is something that we should tell, that there is this restart capability. So you can run for 2 million steps. Then you can take that configuration, and it's already demonstrated. Because demonstrated, I am sure Mohan has also demonstrated. So you take that 2 million time step, again you input that, and you go further 2 million, and you go further 2 million. That is also possible instead of running a full 6 million time step simulation.
So function F3, same as the last time. All
Yes.
this will, nothing will change here other than the filling.
Yeah, that's some important.
Same temperature, so we'll give the same values for C equilibrium, C fill, and C gas. So boundary conditions are always periodic, but we don't have to worry about that since we will force periodic in any case.
Important.
I will show how to add a random cylinder for ours. It's the same as the other modules. So we'll add it for beta here. We will give a precipitate radius of average precipitate radius of 8, volume fraction of 0.1, shielding distance of 3 times radius, and variation of 0.1. So that's 10%. So our epsilon will be 4e minus 9, which is 8 grid points. 550 equilibrium temperature, 450 simulation temperature, tau of 5e13, and we'll track the simulation every 1000
So
seconds.
remember the value of tau that we have chosen, tau equal to 5e13, is basically to ensure that it is a diffusion control coarsening. It's all, there is no interface control.
Generate the files now. This time I'll call it LZN multi, since we have multiple particles, and F03. Generate the files. So I won't generate again, we already have that.
It will take little time to load. But it will work, and you will see very nice coarsening. And then we have the multi-stages. So we want to also show a multi-step coarsening, multi-step aging simulation. Input.in. By the way, this is something that I will tell the time that these files are loading. You think of this from yesterday onwards. We have shown full MPI. We have shown OpenCL. Now we are showing multi GPU MPI. I don't think any tool exists till date which has this many capabilities. So multi GPU MPI, and in OpenCL also is a multi GPU MPI, and then you have also multi CPU MPI. So you have a CPU GPU hybrid which is massively parallel. So I really not know whether even commercial software, just as far as I saw, I looked at this NVIDIA list and all. I saw ANSYS Fluent offers a little bit of that, but that's also very restricted, node restricted and stuff. And that is not, and all these micros and stuff I don't know, but I am sure that there is no single GPU is there. A single disk. So the point is that this is that way a very nice massively parallel code which you can run on your clusters, and also you can run on the NSN clusters if you have computational time. And the later thing that we are going to develop in the next the recrystallization grain growth modules. That will also be this multi GPU MPI version will be there. Multi CPU MPI version will be there, and yeah, it's working.
It's still loading. I thought meanwhile I can open some other. So you can continue. Sorry.
No, you can.
I was just getting ready for the next one.
Okay. Yeah. So one small thing, yeah, we have to tell that these codes are because we had to run with these clusters and stuff. So today I'm really sorry for this inconvenience that we could not run it on our desktop or laptop. So that is one problem that is there, and it took a lot of time to get the GUI working properly there. So yeah, so let us just see. Let us hope that
it's still loading. It's a lot.
Ah,
Because
so-
to see coarsening, we had to wait a lot.
Yeah, it's a 6 million steps simulation, so it is taking some time, 300 files. So, but again, maybe one of the things that we can do is we have to do that. Only thing is the network is also an issue to generate, to take all these files, SCP them to and put it there. Maybe later we will have a centralized data server or something that we have to put. Or, because remember that the amount of the size the size that we can handle is much bigger that I think even any current phase field software can handle. That is another very important thing I have to tell you. Even if you look at moves that we have looked at moves and prisms, we found that yeah, those are also very powerful finite element based software, but there is a tremendous size restriction, particularly when you go to 3D. It becomes extremely difficult. So this is my own from my own experience. I'm telling it becomes very difficult to handle the data, and the number of that adaptivity also becomes very complex, and it slows down many things. So most of the move simulations, if you have looked at or visited their sites, restrict to small two-dimensional systems. Some are 3D, but that require a huge amount of massive amount of CPUs, and they do not still have GPU capability. Yeah, then we run.
So while it's running, I thought we can run ternary. We
Okay.
can show ternary.
So let us do the ternary. Yeah. So we will. Yeah, that's a good idea. Ternary we have already run. We just directly want to go to we again want to show the input file. Let us show the input file first. Then we will directly go to the data file. So ternary, remember, so we are again looking at gamma prime type of system where it is NILMO. In this case, we do not have the open database, so we used a encrypted database to generate this CSV files. The CSV files will contain the information of the curvatures at different temperature, how the curvatures change, curvatures of the free energies change of gamma and gamma prime at different as a function of temperature, and how and all the phase compositions. Okay, all the phase compositions of gamma prime and gamma. Gamma is the parent phase. Okay, so gamma is listed in the last column. So the nickel is the dependent variable. Aluminium and molybdenum are the independent compositions. So aluminium and molybdenum in gamma prime. So there will be 5 columns in this file, and we have the CSV file.
Yes.
Yeah, can we just open?
The CSV files are there in the repository for this particular.
Yeah, so we open it,
template.
so we can show. I am telling, so we can show and tell. Yeah, so as you can see here, this is how. So from temperature 800, we have gone up to temperature 1200 at steps of 10 degrees, and we have the gamma prime. If you see that this is the gamma prime composition, aluminium and molybdenum, and the next 2 columns are the gamma compositions. Remember, when you generate, I think it's all automated. So when you generate the CSV files, the gamma, that is the parent phase, should always be in the last. Means it has to be listed in the last 2. Means whatever columns it is. It depends on the number of k-1. Means if your k-1 is, if it is NILMO, it is like ALNMO. If it is NILMO CR, it will be like ALMO CR on this column. So that's the idea. So so let us.
So these are the curvatures.
So and this is the HSN. This is another CSV file which lists the curvatures as a function of temperature, again at steps of 10 Kelvin. Okay, so for the
second column will be dou square g by dou c a square. Second one will be dou square g by dou c b square.
And then that is the dou square g by dou c b dou c c. And as you know, dou square g by dou c b dou c c is the same as dou square g by dou c c dou c b, because g is exact differential.
So for the ternary simulation, we will take this 500 square domain.
Yeah.
Again, the same dx dy of 0.5 nanometers.
Means we have chosen 0.5 nanometers. It's not that you have to choose 0.5 nanometers. You can also choose 0.25 nanometers or 1 nanometer or 2 nanometers. Accordingly, you can also choose an epsilon. So that, remember, this is one thing in phase field. We generally want to resolve the interface width, means whatever interface width we choose, by at least a number of at least 8 grid points to be on the safer side. Even 6 grid points work, but I think to be the more the better.
So again, we have alpha as the matrix phase and beta as the precipitate. We have 3 components now: aluminium, molybdenum, nickel.
So nickel is the dependent. So here you will see that nickel is a dependent variable. Aluminium and molybdenum are the independent concentrations. Now go next. It's okay. It's okay. We finish one. Yeah. This is already loaded. That's what you're telling.
Yeah, it's a loaded one. I'm opening a loaded one. This is just a glitch.
No. Is the portioning thing already finished?
Almost.
So let us continue, no?
Yes.
Then why did you switch?
Oh, because of,
It's okay. So continue. Tell time steps. We have taken time steps up. No.
we can. So no, the SIN file has only 1000. In the actual simulation, I've taken, I think around
1 million. 200,000 time steps. What instances did we save? At every 100 steps we have saved, huh?
Every 1000
steps we have saved. Okay. Now let us look at the diffusivities. Let us look at the diffusive matrix. Now you see.
So here we need.
Yeah, you need now D. There are, so for each element, right? So you can discuss.
So it'll be so since
we are taking diagonal diffusivities.
Yeah.
We are not taking the off diagonal term. So you have
d alpha 1 and d alpha 2.
So remember, here we have taken equal, but you can take unequal diffusivities. Does not matter. Only thing is, as you know, that the fastest step will determine the delta t. The fastest diffusion species will determine the delta t, and the slowest species will determine the rate, means the rate of the growth of the precipitate.
So gamma we have taken 0.12484 joules per meter square. That is, and then 8.314 for R and
molar volume we have taken
9.6 E minus 6.
9.6 E minus 6
meter cube per mole. Here we have to choose function F4 since we don't have the open TDB.
So this is a very important thing. When you do not have open TDB, already Abhik has shown several instances of that. If you do not have open TDB, you have to use function F4. You cannot use function F3 because there is no TDB file to read. It's an encrypted TDB.
So this is just a placeholder value. I won't read that. So now we have.
What is this value? So the TDB name. Yeah, TDB name is just a placeholder value when you use a function F4.
So the TDB phases here in this file have been named L1 to FCC A1 for the. This is the gamma phase, and this is the gamma prime phase.
A1 FCC A1 is the gamma prime. FCC A1 is the gamma phase. FCC L12 is the gamma prime phase. Yeah.
So the phase map will reflect that, since alpha beta will map directly there. Phase compositions, again you have to give 2 for each. You have to give a tuple of 2 for each phase combination.
So exactly, the number of components as you increase, you have to just increase the tuple size.
So k minus 1 size.
K minus 1 tuple.
So here C gas doesn't matter. So this is again a placeholder value. We need C equilibrium and C fill for the filling. So I have filled at 1200 Kelvin. Again, periodic everything. We will add a single cylinder. That is buggy. So again, ASCII binary we can choose. Track progress I can give higher, say 1000. So tau we can give 5E13. epsilon of 4e minus 9. Equilibrium temperature we can give.
That means 4 nanometers is the bit of the interface.
Equilibrium temperature will be 1200 Kelvin, and we'll run it at 1100 Kelvin. So I have already generated everything.
So go back and just do the.
Yeah, so this is the coarsening simulation.
So let us go back to the coarsening simulation that we left. So let us go to the beta. First, let us see the beta map. The beta phase is the precipitate phase. Now let us run the movie. No, let us run the movie first. Can you make it full screen or something?
No, so this is the maximum.
The maximum. I can't see there. I can't see here. It's very really bad. It's running.
Yeah, it will grow for a while.
It has started coarsening, but it is also growing. Some of these are growing. So it's not fully, completely the supersaturation is not. I can't see that much. I think something is there with the light.
We have this light on that side.
I think
We cannot turn it off.
Okay. Can you just?
You can jump to some later steps.
Can you jump? Yeah.
There's a fast forward button.
Yeah, just use the fast forward button.
Just pause. I'm waiting for pause to take.
Oh, why?
Fast forward.
Huh.
This is the last.
Yeah, this is the last.
Yeah. So you can see a lot of coarsening, but there is also some impingement that has happened. It's not that we have a. Actually, you have to understand the undercooling is pretty high here, 100 Kelvin. So you can understand that there is a lot of supersaturation there, and we had a volume, right? We had
0.1 volume fraction.
Yeah. So now let us look at the radius and all this area measurement and stuff. No, first go to the radius. Go to the radius. It will come very nicely.
Yes.
We should have done precipitate. Yeah, count is also nice, but
Since there is a lot of data, let's see 605 this side.
no, it's not that it takes so much time. It is basically because we are doing it over the net. That is why you are seeing it. But if it is done, for example, if I were in IIT means I was in IIT Hyderabad or he was there, it would have been like pretty fast. We are doing like 2 VPNs here. We are logged into Param Seva. From Param Seva, we are logged into our cluster, and where we are doing the visualization. So in Param Seva, basically we run the. So the idea is in NSM nodes, we have to run our simulations and we have to visualize in our cluster. That is the idea. So the entire NSM concept is that NSM does not provide any visualization nodes. So that's why this. Can is it happening something?
Yeah, it's going to be very slow.
Very slow. No?
Yeah.
So let us okay. No. If you so now there is another. We are now scared to open the other tool because
We can go to while that's loading. Simulation.
yeah. So he also has more courage than I have, so he can do all this. So the only problem that we faced here, to be frank, is this network issue. Otherwise, things were running pretty smoothly there. So, and it's this transferring. Please remember, GUI tool is pretty fast. It's actually one of the. In fact, what we found is in ParaView, if we have to load this and do this visualization and movie, it is actually much slower than this tool. So this tool is really efficient. That's what we enjoyed also yesterday. However, what's happening is suddenly the network goes down, means it becomes slow, and you see this lot of buffering happens inside. So this is why this lag is happening. Today morning also we saw, right, that this radius was coming very fast. Now what is happening? And this big size. So can we please try that once more? Oh, you will run it now.
Yeah.
Okay. So now again we have there is a track change. Remember, this is the single precipitate growth simulation with 3 components. Okay, NIL, MO. This is the case.
Oh, I have the data. It's there actually here.
Okay, you will run it now.
Yeah. No, I have the data on the visualization server.
Yeah. So can you just see what has happened to the other one? So it's there. So you can see clearly. So good. Thank God that it has come. This precipitate. This is the count of precipitate. As the coarsening happens, you can see the count is decreasing, and you can actually the precipitate count now at these states at 6 million steps. Is what it is?
313.
313.
Sir, people online will not be able to hear if you go there.
Okay, but yeah, I am. Yeah.
Repeat it again.
So the number of if you look at the right hand side plot, can you please tell?
Yeah.
Yeah.
So this is the precipitant count against versus iterations. So this
So
is
you
iterations
start
is
with
6
how many
million.
particles you start with?
Yeah, so we start with around 520 particles. So over time, with coarsening, you can see it's going down. First, there's a small growth regime, after which the coarsening starts.
It has reduced to
Yeah, after around 2 million iterations, you can see that it starts coarsening a lot faster. Because since you started with particles of similar size, they will all start coarsening at around the same time in such a big domain.
Yes. So you can see some 313 particles.
It's almost it's almost 40% lower after 6 million iterations.
Yeah.
6 million iterations at our time step was 5e minus 8. So 5e minus 8 into 1e minus 1e 7, 1e 6 would be around 0.05 seconds of total simulation.
Let's go to the precipitate size. So precipitate size, you will get the entire size distribution. You will identify all these particles. It's a very nice tool. It gives you the area of the particles. It gives you the sizes of the particles. It shows you how it changes also. It's how the size distribution itself changes. So basically, in one tool, you have everything. You can basically study coarsening. You can study growth. You can study Gibbs-Thompson effect. You can study how the number density changes, because number density is a very important parameter, as you know, industrially, particularly for superalloys. Because coarsening what happens. So remember, if you think of this, if you go further, why is this very important? Because if you want to study how this precipitates, these precipitates are harder particles which basically act as obstacles to dislocations and stuff. So if the precipitates start coarsening, they are also moving apart. As they are moving apart, dislocations are free to move, and the systems becomes softer. So so it becomes softer, and it loses its strength. So we have to the design aspect, when the industries want to use it for design, they want to basically see for different compositions and different processing conditions. So this is the important thing that I want to tell about FNF4. FNF4 gives you a tool by which you don't just do isothermal coarsening simulation, but you can do a continuous cooling. You can also do step aging. Say, for example, you want to do many times, if you look at any superalloy industries into superalloys, for example, our defense industries, or even companies like General Electric and all, so that they are interested that how to basically have an optimized size distribution. Which, please open the tool and
Still loading.
okay. So how to basically control this size distribution and have a more or less LSW type distribution, but slightly narrower. Because if you have a narrower distribution, as you can see, coarsening will not take place too much, and then your number density does not change too much, and you can retain the strength for a very long time. Even for thermal degradation and everything, it is very important. So industries can use this tool, one tool, to look at the process microstructure or design the process means the processes so that they can get optimum microstructures and these optimum microstructures can happen via multi-step aging. Many a times what happens in industries, that's what I wanted to talk about the super-alloy industries. Many a times you go super solvers and then you go sub solvers and then you go another sub solvers. Means once you go sub solvers, then you go further down and again you come back a little bit. So that you have different types of distribution of precipitates, which is only thing we do not yet have is the nuclear, means we are not having the nucleation, but we can create, means here we are creating nuclei, but we can also put a nucleation rate, and once we put that nucleation rate, then this tool will be very ready to do this type of experiments online. Means you can do this type of experiments virtually, and once you have done this type of experiments and this is my optimum size distribution that I should require for my service conditions, then you can basically directly use that using this tool. So that way it's a very useful tool which can do all this stuff. So now please have a look. So please highlight the radius, click on that. So go down, so you can see for each particle it has been okay, plot it then. Yeah. So you can see. So that's really nice tool. So let us do the nickel aluminum molybdenum. So you can also do the area if you want to. That's okay. We can come back to this later. Let us go to the NILM
area.
Area. Okay. So the area distribution.
Okay. So NILM have given all the required arguments.
So we are doing it for N2 here, just for demonstration purpose. Please note that you can do anything, right? N8, 12.
Yes.
Yeah. So there is no,
Multi-phase,
as long as many GPUs are available, okay, there is no problem, and I think we get a very good weak scaling, right?
I've seen for 8 GPUs, I saw about 5.5 times performance.
Yeah. So 8 GPUs give us a 5.5 times speed up. So we get a really good quick scaling. So let us. No, but we already have some generated data.
I just wanted to show how it will look.
So yeah, so you will have aluminum and molybdenum that are evolving. You can see. Yeah, very good. So let us go to that one.
Clear here.
Yeah. Use the same. Let us use this same instance. Let's not. Yeah, because anyway, every time we are opening an instance, it is. Oh, you will not show the multi-step quenching.
He said we're running out of time.
Multi-step quenching will show.
No, you can show. I just said, to speed up things a bit.
Oh, okay. Yeah, because things again, we are very sorry for that. Both are sorry for that because we had some network issues.
Yes, it's very slow.
Yeah. So only thing I want to emphasize, every time we are telling very slow, it's the network which is slow. It's not the tool which is slow.
Yeah, the very few time steps, it will load quickly.
Yeah. Okay, all the example, by the way, all the example files with the input file filling.in everything will be given in the repository as examples.
You have already uploaded.
Yeah, it's already uploaded. Yes. So that's it. So I am just telling. The only thing that is still buggy in our thing is the FNF2, and we are means the multi-phase one. So that's what we are trying to fix as quickly as possible. A Newton solver. I think Mohan also faces the. We have to reduce our time step to a very low value. So in a but it you will go to like 3 orders of magnitude. Yeah. Okay. So
This is
you
the area
show,
plot.
no, but you did not show the movie.
Show the movie.
First you grow the precipitation, then only you do all this area. It grows, no?
Yeah.
No, it's okay. Okay, accelerate. Accelerate means no, not the end time.
No, it takes. By the time I paused, we almost reached the end.
No, why did you go pause?
Yeah.
Run it.
No, this is all we have right now.
Okay. Now show the.
This is for 200,000 steps.
Yeah. So just show the precipitate size. No, we will show all the plots together. That is also possible, which is quite nice. So we'll do plot all. We'll do plot all.
Okay, plot. Area won't come in this.
Yes, it will come. Area is there. Area is the plot all. You can see that the radius, although because we have grown for a little less time, but you can see that it is parabolic, and you can see the area is a straight line. Aspect ratio is perfect 1.0. So that's what I also wanted to show. So it's really nice. So if you want to show the multi-step edging, we can quickly show. We just rush through the in file. So can you? Yeah. So that's the only thing that. Let's show the results. Multi-step edging, you have the results, no?
Yeah.
Yeah. Just.
So the composition plots for.
Composition plots also. Yeah.
But I cleared already.
So yeah. Anyway, all of these things will be there. Composition plots also will be there, so you'll be able to see that. Really, we had to rush a little bit. We apologize for this. Anyway. Yeah, go ahead. So if you can show that simulation, you can quickly show maybe in another 2 minutes. Please step aging.
Yes.
Hello, sir. This is
I have a
Akash.
video for it.
So let's show the video. Let's show the video because this takes time to load files. The brain problem is the loading.
I'll have to close the tool then.
It's okay. Just show the video. But anyway, the tool can be used by users, right? Since it's all there. So what are we doing here? Just
yeah.
At some point, we will take the things and further.
Yeah.
So you tell now first. So
yeah. So this aging, it was done for around 1.2 million time steps after 500,000 times. So for the first 500,000 time steps, I ran a multi-particle system for at 500 Kelvin, where equilibrium temperature is 550 Kelvin. Next 500,000 time steps, I ran it at 450 Kelvin. No, it's a lag effect. No, it's a lag effect.
oh my god! But this how big is the size?
Very small.
But then
because it has to use the windowing system to. It should tell my system to.
Yeah. So this is the problem with GUIs over internet.
It has to download the entire thing. That's the issue. The video has to be downloaded. There's no running around that.
Oh, it has.
Yes, because pixel for pixel, it has to replicate.
But yeah, the simulations are interesting, but yeah, problem was
Hello.
it's loading. See, the problem is that it has to, as he told, it has to download the entire file, then only it can.
Maybe easier to SCP.
First SCP, exactly. That's what I was thinking. You are running on the server.
Yeah. No.
GLC cannot run.
No, I did that in the morning. It was faster than this.
Because morning network is generally
Yes.
not so clogged. I don't know for what reason, but yeah. We'll finish it in another 1 minute. I'm sorry for this. Hey, please.
Yes.
I'm angry. Yeah. It's some 40 MB, 50 MB file.
No, 1 or 2 MB.
Then
Network.
how much time? 28 KB.
Not in 1 MB.
Actually, here somehow this IIC LAN is no. That's running. Running.
Yeah, it's running.
Yeah.
It will be at around 25 seconds.
So basically you will suddenly see also
Yeah.
super saturation. Again it starts growing. So it's coarsening. Now you go down. Again these guys will start. You will see some growth. So we could clearly see that with the tool, it's very clear to. It's very easy to detect that. But here it's like running at a go. So you are. It's almost undetectable.
This.
No, it's there. You can go in the middle. Somewhere changes, no?
I have better data on my laptop, which will run very quickly. Just a minute.
You skipped lot of steps when you created the VLC.
The VLC I created 5 minutes before the presentation.
So that's the problem. So that's it. So there are lots of steps that.
This one is also a quenching simulation. At around 50 time steps, you'll see. I'll slow it down. So you can see this is when the temperature is reduced. This is the same simulation. I've just run it on a smaller system.
Yeah, that's right. This impingement happened because it ran on a smaller system with a similar error. So it gives some soft impingement, but it's also you can definitely see the coarsening. And
so I ran it for around 500,000 time steps at 500 Kelvin, then 1 million time steps at 450 Kelvin, and after 1.5 million time steps, I changed it to 400 Kelvin.
But the super saturation goes up now. Where is that?
At this point.
I'm not able to see the contrast.
So this is when the temperature change happens. You can see the interface shifting itself to the new equilibrium.
But it also shows, if I remember yesterday, it was showing some growth also, right? It showed as soon as, because you are creating a super saturation. So this again we have to use that tool. The tool will give you a very accurate way that there is the super saturation again getting created and there is a growth. So we could not use that tool unfortunately for this last month, but all are there in the examples repository. So if you have any question, I think it's already very late. But anyway, you please mail us and we will also explain. And another very important thing, because this is a new thing that we are showing, this CUDA aware MPI and all this stuff, maybe you will require some help, means the users who are there may require some help for compilation and stuff. So me and Shorav are ready to help there. So if you have such systems where you have multiple GPUs and you want to run these codes and test these codes for your particular system of choice or whichever systems, please do contact us by email also, and we will try to help you as much as possible, so that quickly you can run this compile these codes and run them. Okay.
Yeah, so we'll take questions at the end of the session today, right? End of the session today. Any questions? End of the workshop.
End of the workshop.
So we can break for lunch now. Yeah. Okay. Yeah. Thank you for listening. Sorry about the delay.